welcome to this session. Now, we will be, as we have discussed in the last class, that another typical filtration physical phenomena occurring in membrane filtration is gel formation over the membrane surface. Now, in the last class we have seen how the gel is formed over the membrane surface. There are two ways. One, the filtration may be osmotic pressure controlled initially, later on it can get transition into the gel layer controlling phenomena. In a second case, there may be solutes which will be gel forming from the very beginning of the process, like polyvinyl alcohol, pectin, and which are known as the well known gel forming agents. So, in this class we will be looking into the various modeling approaches of the gel layer controlling filtration. The first one will be looking into the steady state model, and this will be same as one dimensional film theory model. That we have considered in the in case of osmotic pressure control filtration. We assume a constant film of thickness delta, constant film of solutes of thickness delta is formed over the membrane surface, and it will be having a constant solute concentration within the gel. So, Cg is known as the gel layer concentration, and at the steady state there will be a there will be a constant growth of mass transfer boundary layer over this. So, this will be actually the delta, the mass transfer boundary layer, and this will be the gel thickness. So, this is the thickness of mass transfer boundary layer, this is the gel thickness, and we assume that the solute will be suffering a concentration gradient or polarization from the bulk at C naught to gel solution interface, that is gel concentration, and then the concentration of gel remains same within the gel layer, then you will be getting the permeate flux. Now, at the steady state we can write down the solute balance within this mass transfer boundary layer. If you write a solute balance in mass transfer boundary layer, then we will be getting VW C plus D dC dy will be equal to 0. There is no solute concentration in the permeate stream in this case, because in most of the cases the gel forming material are larger in size, they will be having bigger sizes and the larger molecular weight, and typically they will be retained by the membrane surface, and the permeate concentration is 0 in most of the cases. So, if you really carry out this integral from 0 to delta with the variation of concentration from Cg to C naught, then you will be getting Vw is equal to K ln Cg by C naught. So, this is the steady state equation of the permeate flux in the gel polarization case, and mass transfer coefficient can be estimated depending on the domain of the flow domain as well as the whether it will be a laminar flow or turbulent flow, and or whether you will be working with a tubular module or whether working with a flat sheet geometry or hollow fiber module. So, depending on the module as well as the flow domain, mass transfer coefficient will be evaluated, whether it is a start cell, whether in the start cell are less than Reynolds number less than 32,000, above 32,000. All those correlations we have already correlations of mass transfer coefficient we have already discussed earlier. Those are coming from the heat and mass transfer analogy will be valid, and depending on the flow domain and the flow geometry, one will be estimating the mass transfer coefficient. Once the mass transfer coefficient will be estimated, the gel layer concentration, if the gel layer concentration is known to you, then one can estimate the permeate flux at the steady state. Now, let us look into the so what is the typical parameter in this case? The typical parameter in this case is the gel layer concentration. How to evaluate the gel layer concentration? So, it is very easy to evaluate the gel layer concentration. The governing equation for calculating or estimating the gel layer concentration Cg is this steady state equation. So, we conduct the experiment at different concentration of the feed solute and then measure the permeate flux at a particular k. K means at a particular turbulence. So, we plot then VW versus feed concentration in a log scale. This will be a log scale ln C naught, and then we will be seeing that permeate flux will be decreasing as the feed concentration increases. So, it will be a straight line, and we extrapolate this line, and where it cuts the gel layer in y equal to where it cuts the x axis, that concentration is the gel layer concentration. So, when C naught is equal to C g, ln 1 will be equal to 0. So, you will be getting the 0 value of flux there, but in an actual experiment you will be always getting some value of finite value of flux. So, therefore, this line will be extrapolated and you will be getting the gel layer concentration. If you conduct the same set of experiment with another value of turbulence or the mass transfer coefficient, then you will be getting another. So, but if we extrapolate, that will be boiled down into the same value of C g. So, that is how the gel layer concentration can be obtained experimentally, and this parameter can be estimated. So, once you estimate the parameter, the gel layer concentration can be put, you know the unknown value of for a known value of C naught, then you will be getting the value of permeate flux, knowing the estimating the mass transfer coefficient. But remember, in case of gel layer control filtration, controlling case, C g must be very high, and sometimes C g is around maybe as high as 150 times to 200 times of C naught. That means, in a gel layer control filtration, the concentration suffers maximum from within the mass transfer boundary layer from C naught to C g, and sometimes C g can be as high as 150 times to 200 times of feed bulk concentration. Therefore, variation of the transport coefficients will be extremely high in case of gel layer control filtration compared to the osmotic pressure control filtration. So, and as we have discussed, there are 3 major parameters which will be appearing in your system are the transport coefficients. One is the density, viscosity and diffusivity. Density is the weakest function of concentration, diffusivity is a little bit stronger, viscosity is the strongest function of concentration, and typically viscosity varies exponentially with concentration. So, therefore, correction by Siderted correction factor is very important in case of the gel layer control filtration, and one can get a correction factor something like this 1.85 Reynolds Schmidt d by L for the laminar flow in a rectangular channel, Schmidt at bulk divided by Schmidt at the wall. So, raised to the power 0.27. What is sometimes this Schmidt number ratio can be approximated as mu at bulk divided by mu at wall, because if variation of diffusivity and density are minimal, then it will be mainly the variation of viscosity. And mu at bulk means mu is evaluated at bulk concentration, that is C bulk or C naught. As we have discussed, C naught is the bulk concentration in this case, and mu at wall will be nothing but mu evaluated at gel layer concentration. Then, as we have discussed earlier, that since this value is viscosity is increasing with concentration and C gel is always greater than C naught, the denominator will be always greater than numerator, and it will be basically the value of mass transfer coefficient will be decreased because of the variation of the properties in the mass transfer boundary layer. Hence, one has to invoke the Siderted correction factor in order to estimate mass transfer coefficient in case of gel layer control filtration, because here the concentration variation is the maximum, therefore, leading to the maximum variation of the thermophysical or transport coefficients or transport properties. So, this is a must in case of this correction factor is a must in case of gel layer control filtration compared to the osmotic pressure control filtration. Now, next we will be looking into a most likely gel polarized filtration case. Filtration. So, what is that? We will be having a membrane, there is a formation of gel over it, and over there will be formation of mass transfer boundary layer because of the external flow. So, C is equal to C naught here, C is equal to C g here, and C g remains same in the gel layer. And if you put your axis at y equal to 0, this will be y is equal to delta, where delta is the thickness of the mass transfer boundary layer, and then this will be y is equal to delta plus L, where L is the thickness of gel layer at any point of time, and then you will be getting a permeate flux. As time progresses, this gel layer grows in the y direction, and your thickness, which will be essentially a function of time. So, therefore, this thickness L, it increases with time. So, if you look into the value, so variation, the gel layer thickness grows with time, and then it will be reaching a steady state, probably because of the existence of external flow. And as you have seen that there will be two resistance, there will be three resistance acting in tandem in this case. One is the mass transfer boundary layer resistance, mass transfer resistance, another is the gel layer resistance, another is the membrane resistance. So, these three resistances are acting in tandem here, and since the gel layer resistance is increasing as a function of time, this membrane resistance will be remaining constant, and mass transfer boundary layer will also be remaining constant, and then you will be getting a constant decrease in permeate flux. So, this is how the permeate flux varying with time, this is how the gel grows in time. When gel layer thickness becomes constant steady state, permeate flux also becomes steady state. So, we are talking about a system where it is a moving boundary, because L is growing as a function of time, the value of L is increasing. So, it the boundary is moving, we are talking about a moving boundary system. So, now we write down the mass balance equation within the mass transfer boundary layer. So, solute balance equation we write. So, this becomes rho g dl dt, this is the accumulation term, is equal to V w c minus d dc dy, and the boundary condition it should satisfy is that at y equal to 0, c is equal to c naught, and we evaluate at y equal to delta, c is equal to c g. So, within these two boundaries we evaluate this, and if you look into this type of this equation, now here L is a sole function of time, sole function of t. So, L is a sole function of time, and c is a function of y alone. So, because c is the concentration, that is solid concentration that is occurring in the mass transfer boundary layer, and mass transfer boundary layer is entirely depending on the hydrodynamics of the system. So, I can take this, I can do this integration over y, keeping left hand side as constant. So, this can be treated as constant. Therefore, if you can identify this equation, this is a first order ordinary differential equation, but it is a not homogeneous, it is a non homogeneous first order ordinary differential equation, and the non homogeneous term is basically this term rho g dl dt, which will be treated as constant during the integration over y. So, if you really carry out this integration, then ultimately you will be getting rho g dl dt is equal to V w c g minus c naught exponential V w by k 1 minus exponential V w by k. Now, if you look into the steady state, so steady state solution, at the steady state dl dt will be 0, and you will be getting back your steady state solution V w equal to k ln c g by c naught. So, this will be the governing equation of the transient transient value of the gel layer thickness as well as the permeate flux. Now, if you look into the expression of permeate flux as a from the phenomenological point of view, this will be nothing but the driving force divided by the resistance. So, there will be two resistances R m plus R g, the gel layer resistance and membrane resistance, and the mass transfer resistance is already taken care of in the mass transfer coefficient. So, what is R g? R g is known as the gel layer resistance, and what is gel layer resistance? This will be nothing but alpha into 1 minus epsilon g rho g times L. What is alpha? Alpha is called as the known as the specific gel layer resistance. It is a gel characteristic. It is known as the specific gel layer resistance. It has a unit meter per kg. Epsilon g is the gel layer porosity, rho g is gel layer density. Typically, this will be this gel layer density will be slightly higher than the water density, typically around 1015, 1100, 1050 kg per meter cube, like that. And L is the gel layer thickness, which will be essentially a function of time. So, therefore, since L is a function of time, rest are all gel characteristics, VW this Rg will be a function of time. Since L is an increasing function of time, Rg will be also increasing function of time, leading to decrease in permeate flux as a function of operation. So, what is alpha? Alpha is specific gel layer resistance. And these will be obtained from the Kozny-Karman equation as 180 1 minus epsilon g divided by epsilon g cube rho g dp square. So, this comes from Kozny-Karman equation. Classical filtration theory. So, what is rho g is the gel layer density, epsilon is the gel porosity, dp is the diameter of gel forming particles. Sometimes we are talking about the filtration of the polyvinyl alcohol, the polymers. Sometimes we are talking about the filtration of the fruit juice involving pectin, but these polysaccharides of polymers, they will be basically they will not be forming the hard spheres having a definite particle diameter dp. So, they will be forming a very viscous network over the membrane surface, forming which will be calling as gel. Now, dp means it will be the gel layer, that means it will be forming a gel layer which will be equivalent to the resistance offering by particles of average diameter dp. It will be interpreted that way. The Kozny-Karman specific gel layer resistance will be interpreted like that, that although you may not be having exactly well defined particles of diameter dp, it will be the resistance that will be offered by the polysaccharides or polymers, which will be a natural gel forming agent compared which will be so basically they will be offering a gel layer resistance which will be equivalent to a particle having a diameter equivalent diameter dp. So, that will be the interpretation of the specific gel layer resistance. So, now if you look into the governing equation, we have the governing equation of gel layer thickness rho g dl dt is equal to V w C g minus C naught exponential V w by k divided by 1 minus exponential V w by k, and dl and V w is equal to delta p by mu R m plus R g. R g is alpha 1 minus epsilon g rho g times L, where L is a function of time and the governing equation of L is here, and this equation has to be solved at L is equal to at t equal to 0, L is equal to 0. That means, at the starting there is no gel layer thickness. So, this is an ordinary differential equation, but this cannot be solved, this is not linear. This cannot be, because V w will be is appearing on the right hand side. There are 3 places, and V w will be essentially a function of L. So, you will be getting an ordinary differential equation d L dt with a initial condition t equal to 0, L equal to 0. So, one can take recourse to the Runge-Kutta 4 method to solve this equation as a function of time. So, after solution you will be getting L as a function of time. Once you get L as a function of time, insert here. So, you will be getting the permeate flux profile as a function of time. So, this is how the gel layer control filtration will be modeled in an actual scenario. But if you must have understood that there are several parameters, those are appearing in the gel layer controlling filtrations. Next, what we will be looking into this, how to estimate these parameters. Once these parameters are estimated, then only I will be able to solve the governing equation for the gel layer controlling filtration. Now, let us look into the how various parameters are estimated. Now, first let us list down the what are the parameters, those are appearing in the gel layer model. One is the gel concentration, and we have already seen how the gel concentration is estimated, and specific gel layer resistance alpha, epsilon g, dp, epsilon is the gel porosity, dp is the gel forming particle, and rho g is the gel layer density. So, let us find out how the estimation of gel layer concentration we have already done. Now, let us look into the how to estimate the specific gel layer resistance. Alpha. So, for that we have to conduct a separate experiment in a batch cell. And we develop a theory for permeate flux profile, how to obtain in a batch cell, and then we will see how the specific gel layer resistance can be estimated quite easily by conducting a separate set of experiment in the batch cell. Okay. So, in a batch cell, if you write the expression of V w permeate flux, it will be nothing but 1 over A dV dt, where A is the membrane area, or filtration area, V is the cumulative permeate volume, so we can write 1 over A dV dt is equal to delta P divided by mu R m plus R g. So, this is also known as the series model. So, two resistances are acting in series. So, 1 by A dV dt will be is equal to delta P by mu. I take R m outside. So, this becomes non-dimensional R g, and what is V w naught? It is pure water flux, that is nothing but delta P by mu R m. Okay. So, because if there is no solution, only pure water, there is no osmotic pressure, there is no gel layer resistance, nothing. So, you will be getting in delta P by mu R m or L P delta P. So, that is a pure water flux. So, we can write the dV dt 1 over A dV dt is equal to V w naught divided by 1 plus R g by R m. So, next we write down a solute mass balance. Solute mass balance in gel layer. If we really do that, this becomes L A 1 minus epsilon g rho g times C naught times V. V is the cumulative volume of the filtrate. So, at a particular time this much volume has been filtered out. So, that will be carrying C naught concentration of the solute. So, total mass that will be deposited as a gel is C naught times V. So, in terms of the gel properties, it will be gel layer thickness multiplied by area of cross section, that will be a gel layer volume multiplied by 1 minus epsilon g, that will be the actual material that is there in the gel layer multiplied by gel layer density, which is the amount of gel that is presented. So, we can write R g is basically, as we have written earlier, R g is alpha 1 minus epsilon g rho g times L. So, by combining these two, we can get R g is equal to alpha C naught V by A. So, once we get that, we can write the governing equation of cumulative volume as 1 over A dV dt is equal to V w naught divided by 1 plus alpha C naught by A R m times V. Okay. So, we take it on the other side and do the integration. So, it will be 1 plus alpha C naught divided by A R m times V dV is equal to V w naught A dt. This will be integrated from 0 to t, and this will be integrated on the left hand side from 0 to V. So, let us write down what we get after the integration. After the integration, we will be getting V plus alpha C naught divided by 2 A R m times V square A V w naught d t, and then we do a rearrangement to make it linear form of equation. T by V is equal to 1 over A V w naught plus alpha C naught divided by 2 A square V w naught R m times V. Then what we do? We measured the cumulative volume. We conduct an experiment, batch cell experiment, and measure cumulative volume as a function of time, and then plot T by V as a function of V. So, it is y equal to mx plus c. So, you will be getting value, this is for a particular delta p. Okay. So, from the intercept we will be getting 1 over A V w naught, that we can verify, and from the slope we can get alpha C naught divided by 2 A square V w naught R m. So, if you remember that C naught is known to us, that is a fit concentration, membrane resistance is known to us, V w naught is known to us, that is delta p by mu R m. So, that is also known to us. Area is the membrane resistance, membrane area. So, membrane filtration area, so that will be known to us. So, we know everything in this case, slope we have determined. So, we will be getting the value of alpha. So, alpha is determined from the slope. Now, we conduct the experiments for different pressure drop and then carry out the and estimate the value of alpha, then put a correlation of alpha is equal to alpha naught delta p to the power n. So, if n is equal to 0, then the cake or gel is not compressible, it is incompressible. N is equal to 0, incompressible cake or gel. Okay. Otherwise, the gel is compressible, and typically the value of n is less than 1 generally. Okay. It is compressible. So, it gets compressed, its epsilon g or the porosity decreases as we increase the transmembrane pressure drop. So, this is how the parameter specific gel layer resistance is estimated as in case of gel forming gel controlling filtration. In the next class, we will be looking into the estimation of gel layer porosity, gel layer and particle size, equivalent particle diameter for a typical polymeric or polysaccharide gel, and gel density, then that will completely wind up the filtration of gel controlling membrane separation system. Thank you very much.